Okay. Everyone good? Silent. Okay, cool. Hopefully. All right. I did not change the logo, but anyways. So before we get started, right, here's just like a very short table of contents, actually. So we're going to talk about quantum algorithms in general. Then we're going to talk about variational quantum algorithms, and then we're going to talk about a very specific one. Anyways, let's get started. So what is 7 times 5?
21.
Yes, no, it's 35, right? Okay, so what are 2 prime numbers that make up this number? Yeah, okay. Who the fuck is calling me? Hold on. How about this? I mean, but like, you can just do this with a calculator, right? It's not too bad, right? But what if I told you 2 prime numbers, I multiply 2 prime numbers to get this number? See, it's kind of hard to do, right? And that's the point, right? That factoring is like pretty hard. In fact, it's so hard that like most of modern day security is based off of this principle, right? It's called RSA. And you know, the fastest factoring algorithm that we have is basically exponential time. I don't know what the hell they tried to do here, but essentially it's like you pretty much have to brute force like every single combination of numbers in order to kind of like guess and check to figure out what the correct answer is. But then here comes Peter Shor, this guy, with Shor's algorithm. And then basically what his algorithm does, right, is you give it a number, it does some magic, and then you get your prime numbers, right? And it's much faster than this classical algorithm right here. As you can see, that's like polynomial, like polylogarithmic, which is like basically polynomial, and this is, I don't know what the hell that is. Okay. I forgot to add that slide. That's fine. So we welcome to this like paradigm called quantum algorithms, right? Which is basically a class of algorithms that rely on, that kind of exploit physics properties in order to get like noticeable speed ups over classical algorithms. And so some NP-hard problems like you saw earlier can be solved in polynomial or even linear time.
What's NP-hard?
Basically, don't even dream about solving those, basically.
It's like 181.
Yes. 180.
Yeah.
Yeah. Anyways, basically, if you can solve an NP-hard problem, you get a Nobel Prize, so, and $1 million. So, you know, just as a homework question. Anyway, so the basic fundamental unit of computation for classical computers are zeros and ones, right? But in quantum, you have something that's kind of analogous, where you have something called a qubit, which is kind of like a 0 and kind of like a 1. But in fact, these qubits are actually just vectors, right? So this is what a 0 would look like, and that's what a 1 would look like. But the thing about quantum qubits is that you can have something that's kind of in between, like that's neither a 0 or a 1. So I just represented it as an arbitrary vector. And in fact, you can actually think about this as the first number being like the probability that this qubit is a 0, and the bottom one being the probability that your qubit is a 1. And so, in fact, you can also just, you know, if you know linear algebra, you can kind of break this up into these 2 vectors right here, right? And basically, this also describes the probability that you're measuring a 0 or this is a 1. Good so far? Okay, so all of that is to say that you can basically represent quantum like mechanics as a whole with just linear algebra, which is pretty neat. This is what a quantum algorithm kind of looks like as a drawing. So you have some kind of input, you do something to it, and then you measure it. So let's talk about these parts in step by step. So we just talked about the inputs. So as I said earlier, inputs were vectors, right? So what do you do to vectors usually?
Multiply.
With what? Correct. This is what a gate is. It's just a matrix. Yeah, and so at the end of the day, right, after all these like gates, you have like some random ass vector, but you need to somehow be able to like measure the state in order to know something about it. This is kind of physics. It's also like, anyways, I'm gonna kind of brush over the details, but essentially when you measure this quantum state, you kind of like collapse it, right? So if you have a state that I showed earlier, sometimes you'll see a 0 and sometimes you'd see a 1. So some examples are, if you give it the 0 state, then you're always going to see a 0. And if you give it the 1 state, then you're always going to see a 1. But if you give it something that's like in between, then you'll see things that are like 1 half the time and 0 half the time. That makes sense so far? Okay. Anyway, so in summary, what have we learned, right? We learned that qubits are basically just vectors. Algorithms can be represented as circuits, and the operations on these like input qubits are just linear transformations. And finally, you can measure your circuits to get your results. Okay, that's quantum algorithms. But let's look at a case study, right? So imagine you were Shor's algorithm, and you wanted to like get some Robux, and you have to do so by cracking Roblox's very nice RSA encryption, right? So you try to run Shor's algorithm.
What's RSA encryption?
I told you earlier. It's the thing where you like factor numbers.
Oh, okay.
Yeah. You thought you got me there? No.
Oh.
So your computer wants to complain, right? Basically, we can't run this because you need so many qubits, and you also need like a very, very big algorithm. So now your dreams are crushed, and you'll never be able to beat your sister. Unfortunate. All of that is to say, there's no point in doing that. But basically, we can't run any quantum algorithms on the like current hardware that we have right now because we're on the order of like what 400 qubits, and you need like 1 million. So sorry. But you know, we have this thing called variational quantum algorithms. Basically, what these are, right, are, if you remember this diagram, we're just gonna, you know, do that. But no, but actually, this is what a variational quantum algorithm looks like. Does that look familiar at all? You have an input, you have a thing, you have a cost function, and then you have loss talk backwards. So I'm just gonna go over what these two little boxes are. So first we're gonna talk about the onsets. So as we saw earlier, neural networks are controlled by weights, right? You know, you have an input, you do some matrix crap, and you get something. These are weights, right? Similarly, VQAs are also controlled by weights, or parameters, as they're called. So look at these gates. They're controlled by something called theta. And what is theta, right? That thing in the corner. It's a rotation matrix. And as you know, if you have a rotation matrix, you can kind of specify an angle, and that kind of determines how much you're rotating your vector, right? So that's basically it. You have gates that are controlled by parameters, and you can kind of learn these parameters in order to like output the state that you want it to output.
Is like one single theta that controls every single one of them, or
no,
separate thetas?
I just kind of messed up the drawing, but it should be separate.
Okay.
So here's the cost function. So remember this like measurement thing I talked about earlier, right? You have like, you know, sometimes you're going to measure 0, sometimes you're going to measure 1. Turns out that you can actually like measure for basically any type of state, right? You're like, okay, if I want to see the state, I don't know, 0.5, 0.5, then I can be like, okay, so my measurement will always output that state if I wanted to. And I don't know why the slides are like this. Oh, here we go. Okay, so suppose you wanted to measure some 3-qubit state. And then you can set up your measurement device such that whenever you see this thing, all of your devices are like, for each like line is going to output zeros. And so first we're going to measure this a lot of times, right? So you're going to see 101, maybe 10, whatever, right? And at the end of the day, right, you can kind of collect all of those like measurements that you see and then kind of plot it on like a histogram kind of thing, right? So you get some kind of probability distribution, right? But because all you wanted to do is like maximize the probability of seeing this, right? What is the very nice measure for doing that?
Maximum likelihood estimation.
No,
Oh.
It's just that expected value. You know why? Because like, you know, if you just like take the mean of this, right? If you minimize that, then you're going to converge to this number, right? Like, since you want this to be like very high. Yes.
So what if you want to measure like something in the middle, and like it just take the mean, it may just be like the two ends?
Well, the thing is like, you can do this, and then you can just apply a linear transformation to turn it into this state, and then minimize the expected value.
Okay.
Yeah. So because of that, the expected value is usually a pretty good cost function, and there are just certain other ones, but too much math, I don't want to explain it. And so what about the gradient, right? You have this quantum like circuit thing. How are you going to take the gradient? Well, it turns out that you can just kind of approximate it by doing this thing called a parameter shift rule, where you add a little bit of angle, and then you take the measurement and you just subtract it, and that's your gradient. And obviously there are other second order methods, whatever. Jordan's more familiar with this part. And as for optimizer, you could actually just use SGPD and it's pretty good. But there are also other like methods that supposedly do better, but I'm not going to go into those. You can search these up if you're interested.
How do you calculate the gradient?
Yeah, I told you, you just subtract it.
Oh, you do it like
you can just approximate it,
that's
basically.
Awful.
Yeah. But then there's also other like methods that actually don't require gradients. It's basically, I don't know, it's called SPSA, which is like simultaneous perturbation something. But essentially the idea is that you just like, you perturb the system and then you kind of move in that direction. And it actually converges somehow. Okay, so what are the applications of what I just talked about? So here's a graph made by my PI of all VQAs in general. And as you can see, machine learning is actually a pretty big component of it. Like these are basically like a list of 80 papers that we try to find on Google Scholar on this stuff. And especially in machine learning, right? I'm going to talk about the QGAN, which is like GAN but quantum. So I'm going to describe the problem first, and then we can get into the algorithm. So usually, quantum algorithms kind of assume that you can just load in a quantum state and then you can do whatever with it, right? But it turns out that's actually pretty hard to do. You can't just arbitrarily load in state. It's like the fastest known algorithm to do that is exponential time, which kind of like just completely gets rid of like the advantages of quantum computers, right? So the QGAN claims that it can load a quantum state in that corresponds to a target classical probability distribution in polynomial time, which is good because that's much faster than like whatever we had before. So anybody familiar with what the GAN is, or should I go over this? I'll go over it. So this is what a GAN is. You want to generate something essentially, and there are three components. So you have your data, you have a generator, and you have a discriminator. So what the generator tries to do is it tries to mimic that real, like the distribution of the real data that you have in order to like fold the discriminator. And the discriminator's job is to try to call the generator out for its BS, right? And they try to compete, and they basically compete with each other until they kind of reach some kind of equilibrium. And so here's a flow chart. So basically you have a generator, right? You're going to try to generate a probability distribution. And you're going to feed that in with the real one into the discriminator. And then the discriminator is going to try to tell you if it's real or fake. And then eventually, right, when you do this enough times, you get an optimal probability distribution, which you can sample to generate stuff. Okay?
What do you mean by sample?
Like, basically, you have a distribution, right? And then you just kind of like, I don't know, actually, do you know?
Well, okay. In classical GANs, it's just your model is estimating the distribution, like the process of like passing a random initial data in through the model.
Yeah.
That's the sample.
Isn't it in the final layer you have some sort of like latent like distribution thing, and then you just kind of like get an image, and then if you keep generating, right?
Yeah.
You're basically sampling from the model.
So how GANs generate images is when you're training, you're basically feeding it a bunch of like say like a 100-dimensional vector to begin with, and then like it does a bunch of like inverse convolutions and a bunch of other crap and conditioning with other stuff, but eventually it takes that random noise vector and generates an actual image out of it. So your sampling then really becomes, you're just sampling that vector, which is say just from the normal distribution, if that's where you're sampling it from. And what the GAN does is it tries to basically say, like, I'm gonna like push the sampling further. It is the sampler. It becomes the sampler, and when you're sampling from it, it's basically just saying take the random noise and it's going to generate a good looking image. So that's what sampling is. I
mean, I kind of assumed it was kind of like transformers where you have like a thing and you can do whatever, top P, top K, whatever. But maybe that's not the case, whatever. It doesn't matter. So now we have a quantum GAN, right? So there are two setups in literature. You can either replace both of the generator and the discriminator with something quantum, or just the generator. I'm going to talk about the first one. So here's how it works, right? You have a generator, which is just a quantum, like that VQA thing I showed you earlier. It's going to output some kind of quantum state. Then you're going to sample from it, where what that means is you're just going to measure it a bunch of times in order to get a probability distribution. Then you're going to feed that into a discriminator with the actual one. And then it's going to tell you if it's real or fake. And then you can do whatever you want with this quantum state at the end. This is also why we need a quantum thing, because like we want this, and this is not doable with classical GANs.
Wait, why is that not doable with classical GANs?
I mean, it is, but it's like exponential time in order to like simulate a quantum state.
Why is simulating quantum state exponential time?
Okay, there's a lot of math that goes into that, so I don't want to go over it. But it's not, the basic idea is that because a state can be kind of represented as like two numbers, right? If you have like a bigger state, then it kind of like, you have to represent it with 2 to the n like bits. I'm hand waving here, but you can ask me afterwards if you want.
Basically, when we put two quantum states together and they're like now related, you take what's called tensor product of the two. In 2 quantum states, you have 4 entries in your vector. You have 3 of them, you have 8 entries in your vector. 4 of them, you have 16. You can see how that becomes problematic really quickly.
Yeah. Again, you can ask us after if you want. So what are the challenges with quantum algorithms, right? So firstly, these are the 3, right? So you have trainability problems, you have efficiency, you have accuracy. So you have a new trainability problem where when you scale up these algorithms, you can run into something called barren plateaus. And what that means is that your cost landscape kind of like completely flattens out, which means that you can't really descend anywhere, right? You can't do any gradient descent, and so you can't train your model. And there's a lot of places where this can occur. This is still an active area of research, but the way you initialize your like states, the way you kind of set up your onsets, the way you set up your cost function, all of those can kind of induce this kind of problem. Secondly, with efficiency, sometimes it's very hard to get the expectation value. And there are ways that you can kind of deal with it, but again, there are more problems with the ways that you deal with it. So, and finally, because quantum computers are kind of noisy, right? So you can't expect your qubit to always like behave exactly the way you want it to. And so this can kind of slow down your training. It will also bias your cost landscape, which means that it could, corrupt the final value of your cost and also affect your accuracy. And this actually is shown to also induce like this barren plateaus thing I showed you earlier. And so error mitigation becomes pretty important. But again, that causes problems because you need more qubits for this, which means that you're going to have to scale up your quantum computers as well. I didn't put anything to recap, but just to recap, right? So what I introduced was there's some problems in classical computing that are very hard to do, but some of them can be solved with quantum computing, like quantum algorithms. But then quantum algorithms require scale that we don't have so far. So we introduced this thing called VQAs in order to tackle that. VQAs work pretty similar to machine learning, pretty similar to neural networks. And I showed you a specific example of this QGAN thing, where you can basically load in an arbitrary quantum state in polynomial time. And of course, there's still challenges. And this is an active area of research. And this is part of like what I do. Any questions? Yes.
Why does quantum require such a big thing? Seems like the base.
Well, it's because of the hardware, right? So basically how like in quantum computing, like the bits are what you call noisy, which means that they don't always do what you want them to do, which means that you need something called error correction, right? And one of the most popular ways to do error correction is to basically do something called redundancy, which means that you basically have the same thing a lot of times, but because you need a lot of times, right? That means that if your algorithm only requires like, let's say 10 qubits, then if you want to do that like 6 times, right? Then you need 60 qubits, right? I don't know what exactly the math is, but it turns out that you need around like 1 million qubits in order to run that Shor's algorithm I mentioned earlier.
So are we talking about like we just we try to develop a different hardware that we want to be using, or is it just like
I think well, there's 2 things, right? One, you can improve on the software side by reducing the reliance on error correction. or you can get better hardware that's more noise tolerant. Right?
Why are qubits very noisy?
Physics.
Yeah.
Don't want to explain it. I actually don't exactly know, but it's something to do with like the fact that you need to untangle qubits, and then there's some sort of decoherence, whatever. Anyways.
Yeah. I think the number currently is to have a decently error-corrected qubit, you need 1,000 qubits to correct it. So you have a 1,000 to 1 ratio currently of like
Yeah.
a reliable qubit to how many other qubits you need to help it be reliable, which is not great.
Yeah.
How do you figure out how many qubits you need?
I think it also depends on like what you're passing in. Right? If you, I'm not sure what the numbers are for Shor's algorithm, but for this one, this QGAN here, basically, if you want to represent a state that has like, I don't know, like 10 things in it, then you need 10 qubits.
Yeah.
Is that simple? Yeah. Arjun?
So like, you're not passing in, you're not putting images.
You're not.
What does it generate? Like, what are you using that model of that?
Yeah, so you're using it to generate an arbitrary state. And this is like important because a lot of other quantum algorithms, you need this state in order for those algorithms to run. And one of those is called this quantum recommendation system. Honestly, not very useful, but essentially like what this is supposed to do is to speed up what we already have for recommendation systems. I don't know how that works, but yeah.
If the state that you're generating is a quantum state, then to decide whether it's good or not, you need to measure it, which it collapses.
Yeah, so the thing is the generator, like, you're basically actually like modally collapsing it because you only wanted to generate one state. But like the way you tell if it's good or not is through this part, right? Where you basically collapse it to get like probability distribution. But the thing is like if you generate it again, then you get the same state, right?
Oh, I see.
Yeah.
So you
But when you sample, you get something different.
Well, yeah, if you sample it, you're basically getting some real numbers.
I see.
Yeah.
So you're feeding the generator number to regular again?
No, you just feed it all zeros.
Most quantum algorithms just start with all
Yeah.
zeros.
Well, the thing is like you can kind of create your own vector by just doing some gates on it in the beginning.
I'm a little bit unclear as to how this applies to the vectoring task we want to do at the start.
What vectoring task? Oh,
Sure,
factoring?
Choice.
Oh, that's not related.
Um,
The factoring task is just because is to introduce the idea that there are quantum algorithms that can do factoring a lot faster. But in general, there are many other problems that quantum algorithms can do faster than like. So for example, one of them is what was it, max cut, I think. If you haven't taken 180, don't worry about it. But basically, min cut is like, if anyone's taken 180, min cut is solvable in like polynomial time, but max cut is not. And max cut is NP hard, but it's doable with something called QAWA. It's a different algorithm, but I haven't talked about that.
And basically what a max cut is, if I remember correctly, is like if you have a directed graph, you're trying to say, how can I like basically split the graph into two partitions, like all the nodes into two partitions, such that all the connecting edges between like from one of them to another one, like if all the edges are weighted, then you are maximizing those edges.
Yeah.
So you can kind of think of it as like, oh, if I were to split my graph into like two groups of nodes, what is the way to split like I get the most flow between them? Yeah. And it can be, you can see how that's helpful in a lot of like logistics problems and like, network problems. And it is currently like, I think exponential time to solve it.
It's NP hard.
It's NP hard, so yeah, it's pretty much exponential time to solve it. You basically have to like loop through all the combinations.
Yeah, pretty.
Yeah, of like ways to solve the graph.
Yes.
So if quantum algorithms can do like a factoring task a lot faster,
Yeah.
kind of factoring task is kind of like how RSA works.
Yeah.
If quantum becomes mainstream,
Yeah.
would it render RSA useless?
Yeah, we're fucked. That's why there's this thing called post-quantum cryptography, which is like sweaty math people trying to figure out other like problems that quantum computers cannot do. So yeah, the reason why we're still safe is because we cannot make a quantum computer big enough to do this kind of factoring thing. But if we do, then yeah, we do have a problem. Yeah.
How big of a problem?
Well, you have to replace RSA pretty much.
Like all the CDs will become unencrypted.
Yeah.
Most private key, public key becomes
Yeah.
problematic. like most of encryption as we know it today can be broken very easily.
Yeah, that's one of the like main ways they kind of like hype up quantum algorithms. They're like, oh my god, security, we're all going to die. Yeah. Yes.
When you were doing gradient descent and you had that lost landscape,
Mhm.
I guess with neural networks, in the landscape, the dimensions of it represent like weights and biases. But and you're optimizing those. What are you optimizing here?
Yeah. So like I mentioned earlier, right? Where's my slides? I have too many. You have these things called parameters. These are like separate parameters, but I just didn't annotate them. So what you're doing is you're actually finding the gradient with respect to each one of these. And then you're doing the same thing, right? You're just like changing these parameters so that it generates something better.
So what you're optimizing is the value of theta for each rotation gate.
Yeah, essentially. That's why I denoted cost with like data.
Why is it a rotation game, not anything more like fun?
Well, more math. So basically, you saw how I showed what a qubit was in the beginning, right? Where is it? Here. Okay. This has to be a unit vector because you need the probabilities to kind of sum up to 1, essentially.
Yeah. The probability is we say, oh, that's the probability. It's actually a squared. Basically, you take
Yeah.
the value and you square it. That's the actual probability. So you can see how.
Yeah, which is why I represented it like this, right? Because if you square this, you get half. If you square this, you get half. So you have half probability of measuring each thing. But the thing is, wait, sorry, I forgot what your question was.
Oh, about like what gradients is that?
Oh yeah. So because oh wait, no, that was his question. Sorry.
Like, why don't we do something
Yeah.
more fun?
Because you have like unit vectors, right?
Yeah.
You kind of imagine this like vector as living in some sort of sphere, right? Because all you're doing is kind of like changing the direction of the vector because you want to keep it a unit vector. In other words, everything is a rotation in some way. So you can actually build any kind of gate that I made earlier with just those 3 rotation gates. Yeah. It's a universal gate set if like, yeah.
So the VQA, like what was the problem with solving?
The problem it's solving is something called QRAM, which is slides. Sorry. Where is it? Found it. Okay. Basically, this idea that you can just load in any quantum state is an assumption that a lot of papers make when they write their quantum algorithms. But actually, it turns out that that is exponential time in itself. So like you can't just do it. Does that make sense?
How is the VQA like solve that? Like
What do you mean?
how is it allowing you to load this gate?
The fact that it requires only a polynomial number of gates means that the time complexity of that whole algorithm is going to be polynomial and inference time. Does that make sense? It's like if you assume each gate takes 1 unit of time to like run, if you have a polynomial number of gates, let's say, and like you want to load in a 3-qubit state, and then you have like 9 gates, right? Then if each one takes 1 unit of time to run, then the whole algorithm takes 9 units of time to run, right?
Oh, okay. It's just a better way to learn.
Yeah, it's just that it goes from exponential, which is bad because the problem you're trying to solve classically is already exponential, right? Which means that your algorithm, even if it was polynomial, if you have to load in the state to begin with, then it's going to be exponential, which means that the advantage provided by your algorithm becomes nothing, right? Yeah, you have to learn the gate in order to learn how to do this like mapping in polynomial time.
Oh, okay. So you're like to solve an exponential problem, you're using like a small time gradient descent to do the polynomial.
Yeah, basically. Yeah.
So it's basically what the QGAN is trying to do is it's trying to say we have the state distribution that we want, but like we don't know how to get there in non-exponential time. So we're trying to train a network, a circuit that can be constructed in polynomial time, so we can generate this thing that otherwise. Okay.
Yeah.
How do you decide the architecture of like the circuit itself? Like why it there? Why gates there?
I think most of the time, like you just kind of put in something and hope it works. It's the same thing with like again, right? You just kind of have an arbitrary architecture almost, and then you try to see if it works.
Well,
throwing things around. Like, what do you say? Adding
No, actually, just think about it. Like there are like educated guesses where you're like, okay, I think it's gonna work like this, so I'm gonna try this.
so what are some like established architectures that people have been like, oh, this looks okay enough?
We can look at those. It's gonna be kind of hard to look at, but there's something called a hardware efficient ONSA. It's basically, yeah, looks like that. Yeah, I mean, you can try to understand that, but essentially the idea is that you have these rotation gates here. You have some sort of entangling going on, and then you have more rotation. And then you just repeat it. Yeah.
How does having one rotation gate after another differ from just having like a single rotation gate because we're rotating in the rotating?
Oh, these are rotating along one axis, right? I wrote RY because it's rotating on the y-axis, and this is the axis. So
Oh, and
yeah,
the
so
rotations aren't.
yeah, so I skipped over the math for this, but basically you can represent a vector in some sort of 3D space, like a 3D sphere of sorts. It's called a block sphere. And so if you have 3 different rotation gates on each axis, then you can build any rotation gate. That makes sense.
So like, sad I don't really like fully understand this, but like, this is just like speeding up basically again.
No, it's actually like not related to GAN in some way. A GAN does something classical, right? And we're trying to take the concept of a GAN, like this concept of adversarial training, in order to like speed up this quantum problem that we had.
Oh, so it's just like they can work for any quantum field.
No, it's that one problem I described earlier.
Oh.
This thing.
Oh, so it's
This thing.
basically generating that's.
When you say load arbitrary quantum states, what do you mean by that?
So you say, okay, I want the state, I don't know, 0.5 and 0.5.
Yeah.
That's not a valid state, but we're gonna ignore that. If you just be like, okay, so I'm gonna somehow have that in my RAM.
Yeah.
And then like, okay,
You
like,
have a sample from it.
yeah, I just have this state in the beginning.
Yeah.
You can't actually do that.
Oh.
Does that make sense? Or you can do it, but it takes like exponential time.
So like if you want that state to be precisely that, you want to design a circuit around it. This if you just were to design a circuit like exactly, it will be take polynomial time or something like that.
No, it's like if you want to do this step, like go from I want to generate the state.
Yeah.
That process takes exponential time.
Also, the process of generating a state.
Yeah.
Actually takes exponential time. We're basically trying to like approximate it by doing this whole thing. I see that.
So then, like, with the VQAs, then we can actually use the quantum algorithms that are in place for people to assume this.
Depends on which paper you're looking at, right? Because this is polynomial time, but some papers claim that their algorithm runs in like, I don't know, some polynomial, like polylogarithmic or square root of n, whatever. Those are still kind of like not doable because this whole process takes a polynomial time to begin with. But there are a class of papers which I'm still trying to find that like would theoretically work, right? Like if you had something that's maybe like n to the 4 or something, and this process took n squared, then like those papers would be like actually viable, if that makes sense. Yeah.
How would you use this? Like, is it like a consider VQAs for?
Yeah, like you just need a better process than this, but this is still like a very, very like early research state. It's kind of like we're looking at Fortran, but for quantum, right? Yeah.
So like one of the main problems like nowadays is like it's not scalable enough, right? Like so far, like is there some sort of like Moore's law for like quantum? Like
Actually,
is it like improving or is it just like
there is
like,
actually.
like unsolvable problem?
There's something called Mosca's law. Where's Mosca?
Also, I find that very interesting because it's kind of like the rotations are like our linear transformation neural network, and the entanglements are like the nonlinearities.
Basically, yeah. There's actually a class of like classical neural networks. I don't know what happened there, but they're called tensor neural networks that basically take that like property and just be like, it's actually pretty good in classical. I haven't really looked into that, but like that's something you can look into. So yeah, this basically,
entanglement does the linear operations to like two of the states at once or multiple of the states at once, and that like basically makes it that if you do another rotation after, it will be very different because that process like mixes the aka entanglements, and like mathematically it makes it very, very quote unquote non-linear, which is the best analogy I have for it in the context of classical mathematics.
To answer Christoph's question, this is something that this guy at Waterloo proposed. Basically means that in the next 10 years we're kind of fucked. But I don't know if that's true or not.
Is that like, does it have like some like scientific basis, or was he just like, oh, no, it's impossible?
It's a theorem for a reason. I don't know, but also like one thing to note is that our computers have been scaling pretty far. Like I think just last year, IBM released like a 200, maybe like 400 qubit quantum computer, and the year before that was like 200. So it's like, yeah. I don't know if there's a law just yet, but you should just look at it. Yeah. So you can represent. Actually, let me just pull up a picture of a block sphere because I can't draw. Yeah. So yeah, you can think of like, why is the image on the right? Just open this image. God damn. Okay. Close enough. So you can think of like that being like a 0 and that being 1. So if your state was completely pointed downwards, then it's a 1. And it's completely pointed upwards, then it's a 0. So if your like state was kind of like somewhere in between, then if these are your bases of vectors, then you can kind of think about this as like somewhat a 0 because it's kind of in that direction. Yeah. So the data operations yeah. The thing is, this is representing one qubit. If we have a multi-qubit state, then you have that probability distribution. That's not just two numbers. Right? Like you can almost model a one qubit state as like a probability distribution between 0 and 1. So there's still only two numbers. Right? But if you have more qubits, then you have like, what?
Oh, is
that physics?
That's what like game design. It's like people. That's why people like before people represent rotations as like basically like, oh, what's the rotation like this direction, this direction. And basically, if you rotate with like just the right combination of 9 degrees, you can actually lock the gimbals and still lose a degree of freedom. That's why in like game design they use something called quaternions, which is the whole other thing. But basically, it's like they try to make it that. But like when Unity, for example, like, no longer uses just normal rotation matrices. Is that a problem in quantum?
I don't even know what a gimbal is, so maybe.
Okay.
Is this you represent something in real 3D space, or is this a mathematical?
This is a complex space, like complex 2D hybrid space to be precise. But it's basically like you have 3 degrees of freedom because you have complex numbers as well. It's not just real.
What's the third
I think.
Actually, listen. Okay, I've been studying this for a while because like, this is supposed to represent all the possible states a qubit could be in.
Yeah.
Right? A qubit has 2 entries, right?
Yeah.
Each entry is a complex number. Which means there's 4 possible things, like A, B, C, because you have A plus B, I, C plus D, I.
Yeah.
So there's 4 dimensions. And why do you only have 3 here?
I think. I'm not quite sure, but I mean,
there's 4 dimensions. Do we use quaternions for like this guy?
I mean, yeah. I mean, at the end of the day, if it turns out to be only 3 dimensions, then you can just like make one dimension 0, I guess.
Okay,
makes sense. No, you have 3 angles.
Oh, you think? Oh, okay.
Yeah. You have one in the X, one in the Y, one in the Z.
Okay, yeah.
What is it?
Yeah.
How when you're actually
Yeah. Somewhat. It's like if you know how mathematically entanglement is represented, then you can just do it math and not really have to think about entanglement. And also some of these like algorithms like rely on some like specific properties of physics, like interference and stuff, but like those aren't that advanced, right? Like if you just know these specific concepts, then as a computer scientist, like you're able to do this kind of stuff. And also, quantum computing accepts like a wide field. Like you need the chemists because there are problems of chemistry. You need physicists. You need computer scientists to build like the hardware, to build the software and everything. So I think it's interdisciplinary to some degree, but also like you have your own specialized parts that you can work on. Yeah. Yeah. Yeah.
Pull up the normal on paper.
Yeah. Hold on. Control was it control theory or something? No, just put on my drive for it.
This is being recorded.
Yeah, don't worry about it. Okay. Papers. Oh wait, no. This one's the worst one. Okay. Wait, no, what the heck is that? I mean, there's a lot of words, never mind. Let's go to another paper. Yeah, but essentially the idea is that you can have stuff like, I don't know. Well, obviously this is linear algebra, like this is stuff. This is what like a typical class function looks like in a paper. I kind of took all the math because that's not useful to understanding what it is. You can have these things like global class functions, local class functions, more math, more math, more math, more math. Yeah. And also there's this one paper that was talking about that Baron-Pascal's problem. You have to use some like Lie algebra or whatever, some like group theory stuff in order to do it. I'm just like, I don't know. I'll leave that to my PI to yeah. Group theory. There are papers that actually talk about that. And that's one of the projects I'm working on right now. Anyways, more questions? Yeah, QGAN is one specific VQA. VQA is just a general framework, like that thing that looks like a machine learning algorithm. Quantum algorithm. So like, well, I mean, think about it, right? You're training your model to learn, to like, you're varying those parameters, right? Yeah. I don't know, like, ask whoever named it, don't ask me. Yeah.
So if you draw an analogy with classical computers, then the purpose of the VQA would essentially be like setting a bit to either 0 or 1, with like be a 0 or 1, but like instead of
So what do you mean?
Because like it seems to me that the purpose of a VQA is that you set a qubit to the value that you want it to.
I think in general, algorithms, right? You're trying to make the algorithm do something you want it to do, right? Same thing with VQAs.
Oh, I see.
Yeah. I mean, I just set it up in that way just because that's one of the things you can do with it. But there are other applications like that. Yeah.
So why trace?
Why trace?
Yeah.
That's a good question. It's actually to do with like.
Wait, trace is just a diagonal.
Yeah, like the sum of the diagonals.
Yeah, or make this. Yeah.
It has something to do with the inner product, if I remember correctly. And the fun thing about trace is you can it's like circular, so you can like basically move the trace of this times this is like So you can kind of like it's like cyclic.
That's it.
Yeah,
Oh.
kind of weird. Yeah, too bad. Well, why is this paper thing? Okay. Any more questions?